as we just said, is really straightforward. I know that I'm going to do work that then is going to be transferred into elastic potential energy in the spring, that then when they're released is going to be converted into kinetic energy. They give me enough information to do this. Oh wait, the second guy's not moving, sorry.
Wait, we're just talking about A?
This is A first. And so that then is, this is a 3 kilogram one that's moving off at 100. So that's 150 joules, right? Yes. And so I know that, therefore, there must have been 150 joules of elastic potential energy in the spring. Yeah. Therefore, the net work done had to have been at least 150 joules. All right? Okay. Now for B. B's a little trickier. B, we're going to compress it exactly as above again, so that the total kinetic energy, the maximum total kinetic energy is 150 joules. But what I really want to know is, how do these guys move away from each other? Well, think about it. What's the initial momentum?
I knew it has something.
See, this is why we needed the bowling ball. Which I noticed you conveniently placed up on ceiling tiles. Does that mean you just climb up to the ceiling and
No,
set
it's
it up
just
again?
the rope.
Yeah, I don't remember. I was like, you did?
Why?
Why would he do that? It's so dangerous.
Yes. Instead of climbing up on the chair on the table, don't you remember me throwing the bowling ball up into the ceiling?
Okay, momentum.
You easily get those two acts confused.
Falling down on Wesley.
Or like having it stored.
die.
You should have a bowling ball.
Anyways,
I want to make
so before, and by the way, we're in one dimension, right? So it's not two dimensions, it's just along the x-axis. So I'm only going to worry about one dimension. But what's the initial momentum? Zero, right?
Not zero.
So, is momentum conserved?
Yeah.
No velocity.
Once I let go of the masses attached to the spring, am I doing any work on the box block? No.
Are
Is
you
anybody else doing
by
any work?
pulling your hands
No.
away?
Nobody's
Okay.
doing no work.
Nobody's doing no work.
That
So
means everyone's doing work.
total. So is momentum conserved?
Yeah.
Absolutely.
Yes.
Trick question.
Therefore, what's the total momentum going to be?
Zero. So 1 MV. Oh, that's easy. So it'll be 30 equals 1x. So 30 meters per second.
What are you talking about? There's two velocities.
So the velocity of the 3 kilogram ball has to be like almost 3 times faster than the velocity.
Well, and they say the 3 kilogram mass is then released and moves off at the speed of 10 meters per second.
That's the first part. That doesn't matter.
No, on B the spring is compressed the exact same way, except both are let go.
Yes.
Yeah.
It
So
leaves
it's
at 10
30.
meters per second.
So it's 30.
We don't need to know what the actual speed is, do we? We just have to know what it is relative to each other.
Right.
And so the speed of the...
Which that means this V1 equals
You said that was hard.
3 V2s.
Which
Wait, can you
means,
turn
exactly.
the
So
little-
the 1 kilogram ball is moving.
Okay.
They're 3 times faster than the 3 kilogram ball. Right?
Well, I mean, that tells me that this guy's moving 3 times faster than that guy.
Yeah.
But does that tell me the velocity of each mass relative to the cable?
No.
To the cable.
Or that's a typo, it's a table.
I didn't... Oh.
I gave you a
Cable.
Cables aren't the same thing as springs.
I was just going with the popular thought.
Yeah. Did everyone think that meant the spring?
In other words, are we done yet?
Everyone thought the cable meant the
No.
No, we're not done yet.
But we know the total work.
So we just need to find one of the velocities.
Conservation of momentum. No, conservation of energy, I mean.
Yes.
Because
I know,
Shut up.
I know that the total
Making
kinetic,
sense in my head.
the kinetic energy of one plus the kinetic energy of another is going to equal to what?
0.
150.
Wait, why is it 150?
Yeah.
Because we just said that work.
Because
Hey, that's what I did.
if there's no work done, then the compression of the spring is gonna result in the kinetic energy of the two blocks.
Oh,
Right.
but
Just like we found earlier that,
will the kinetic energy of just letting one block go equal the kinetic energy of pushing both in and letting both go?
Yeah, that's
Yes.
my question.
yes,
Okay.
Why?
Because there's no non-conservative forces.
I mean, where did the energy for the kinetic energy moving one block come from?
The spring.
The spring. We
Okay,
didn't work on the
I get
spring.
it, I get it.
We do the same amount of work on the spring,
It's elementary.
Yeah.
the same, okay?
It's just like moving something
Yeah,
around.
try
Half
teaching
of
this
V
to a
squared
third grader and
plus-
see how far you get.
So,
A third grader would understand the whole spinning something around something that's not
oh,
fast.
no, they knew that was coming. Alright,
We could ask him.
By the way-
He's not elementary. I guess he's above that.
by the way, we're gonna use this and substitute in over here, right?
Yeah, we are.
For
Oh,
V1,
man.
we're gonna say that's 3 V2s
Clever.
Yeah.
squared
One. Yes, yes.
plus 1/2
And one.
wait, this is M1, right?
Yeah.
Plus 1/2 M2
V2.
V2 squared equals 150. Now, I know M1 is 1 and M2 is 3, so now I only have one unknown, V2. So I can solve. That's 9 V2 squareds, so that's 4.5 V2 squareds,
Exactly what I meant.
plus, that's 1.5 V2 squareds, is 150. So combine those terms and I get 6 V2 squareds equals 150. So V2 squared is 150 over 6, which is
5.
clearly 26.
Nice.
So V2 is, oh, okay, you're saying V2. V2 is 5-ish.
What was that? That's right. That's right.
You sounded so stupid, so it's okay.
And therefore V1
That was right.
is,
It's probably like 1 point.
I'd say
It's probably
15.
not 15.
It's
Right.